Hi everyone. So in this lecture we're going to put everything together and use diagonalization to solve differential equations in dynamical systems. So this is something where you've seen all of the pieces of the puzzle before, but now we'll put it together so you can see everything in its entirety. So suppose we have this matrix A, and we want to find the solution to the differential equation x prime equals a times x, with an initial value that's given. According to the fundamental theorem of ordinary differential equations, there is a unique solution to this problem, and we're going to use linear algebra to find it. So the first step is going to be to diagonalize A, and to do that, we're going to need to find the eigenvalues and eigenvectors. So let's start by finding the eigenvalues, and to do that, we'll calculate the determinant of A minus lambda I. And so when we do that, we get 2 minus lambda times 1 minus lambda minus 12. And when you expand that and simplify, you'll get lambda squared minus 3 lambda minus 10. And you can factor that as lambda minus 5 times lambda plus 2. And the roots of this polynomial are the eigenvalues, and so we get minus 2 and 5 as the eigenvalues. All right, so the next thing we need to do is go through each eigenvalue and find the corresponding eigenvectors. So let's start with lambda equals minus 2. And in general, you want to look at a minus lambda I. And so when you put in lambda equals minus 2, that becomes a plus 2i. So here is a plus 2i, and when you put that into reduced echelon form, you get this. And the corresponding system of equations just has the one equation, x1 plus 3 halves x2 equals 0, where x2 is a free variable. And so from that, you get that x1 is minus 3 halves times x2, and of course x2 is x2. And so then when you pull that x2 out as a scalar multiple, you get an eigenvector that you can use. And remember that you have the liberty to use any non-zero scalar multiple of that eigenvector, and so like if I don't want that fraction, I can multiply by 2, and that's okay. And so the eigenvector that I'll use for this is minus 3, 2. Okay, and so now we'll move on to the next eigenvalue, lambda equals 5. And for this, the process is the same, but with different numbers. So now we're going to look at a minus 5i, and here's what that is. And then you put that into reduced echelon form. Here it is. And so you get the equation x1 minus 2x2 equals 0, with x2 being free. And from that, you can solve for x, and you can obtain the eigenvector 2, 1. And so now we have two linearly independent eigenvectors, and so we have enough information to describe the diagonalization. We set P to be the matrix whose columns are the eigenvectors, and we set D to be the diagonal matrix whose diagonal entries are the eigenvalues. And notice that they match up. The first column of P is the eigenvector that corresponds to the eigenvalue that's in the first column of D. And it's important that they match up like that, but beyond that, the order doesn't matter. So you could actually have the columns of P in the opposite order, but then you'd also have to have the diagonal entries of D in the opposite order. But if you did swap both of those things, it would be okay. So it is just worth emphasizing that there were a few points in this process where choices were involved, and as a result, the P and the D that diagonalize A are not unique. All right, so now we're ready to move on to step 2. And what happens here is we make the substitution x equals p times y. When you take the derivative of that equation, you get x prime equals p times y prime. And then you want to sub both of these into the equation that we're trying to solve, which is x prime equals a times x. So when you make this substitution, the x prime on the left becomes p times y prime, and the x that's on the right side of the equation gets replaced with py. And now we can take this equation, multiply both sides by p inverse on the left, and then we get a p inverse and a p that cancels on the left. And on the right, we have p inverse ap, which is equal to d, because that's how diagonalization works. And so this means that the equation we end up with is y prime equals d times y. And I'll point out that this step of the process always happens exactly the same way. We didn't do anything that involved the specific numbers in p or d or a. This always happens exactly like this, and so you don't have to keep doing it over and over again. But I do want you to understand how making this substitution gets you from the original equation to this new equation. But then once you do understand it, then I think it's totally fair to just remember that when you make the substitution x equals py, it turns the equation x prime equals ax into the equation y prime equals dy. Okay, so now we can move on to step 3, which is to solve y prime equals dy. And the point is that because D is a diagonal matrix, this is something that can be solved directly. So if we were to write out this differential equations in coordinates, it would look like this. And if we actually do the matrix multiplication out, then we get a system of equations. And in this case, the system is y1 prime equals minus 2 times y1, and y2 prime equals 5 times y2. So there's a couple of things that are great about this system. One thing is that the equations are decoupled, which means that you have one equation that only involves y1, and then another equation that only involves y2. So y1 and y2 aren't interacting with each other. You can solve those equations separately. And then the other thing is that this type of equation, where you have y prime as a constant times y, is a very familiar equation. It's the equation of exponential growth, and so we know how to solve them. So the solution is that y1 is a constant times e to the minus 2t, and y2 is some other constant times e to the 5t. And then, of course, you can express that solution as a vector. So now we can move on to step 4. And what happens there is that now we have our solution for y, we can use that to get the solution for x. And to do that, we just substitute back using the equation that x is equal to p times y. Okay, so here is the matrix P and the y that we found, and we just have to multiply. And when you do that, this is what you get. Now, if you like, you could separate this into terms where one term has a C1, where you can pull that C1 out as a scalar, and then another term has C2, but it's fine to leave it like this if you'd like. Now, what we have found at this point is the general solution to x prime equals ax, and that's why these constants are in there. There is one more step in this problem because we were given an initial value, and that initial value will allow us to solve for these constants. So this was a couple of slides back, so I'll remind you that the initial value was x of 0 equals 3, 5. And so to get x of 0, we just plug t equals 0 into our general solution. And you can see what happens is all of the exponents become e to the 0, which is 1. And so we're just left with minus 3c1 plus 2c2 on top, and 2c1 plus c2 on bottom. And we set that equal to 3, 5, which is our initial value. And now this is just a system of linear equations that you can solve. And that's something that you know how to do pretty well, so I'll leave you to go through the details, but what you end up with is c1 equals 1 and c2 equals 3. And so then we get the final solution to the problem by plugging these values for c1 and c2 into the general solution. And so here it is. This is the unique solution to the differential equation with the given initial value. Now you might remember that when we were doing the diagonalization process, I told you that there were some places where you could have made different choices and you would have ended up with a different p and d. If you had made those different choices, those differences would have persisted in steps 3 and 4, and even at the beginning of step 5. But no matter what choices you made, when you arrived at the final solution, you would have gotten exactly this. This is the unique solution. So one thing that people sometimes ask about these differential equations is what is the asymptotic behavior? Like what happens as t goes to infinity? And something that you can see here is that when t goes to infinity, the e to the minus 2t term will go to 0. And then you're just left with the e to the 5t terms. And this is kind of interesting because you can see that you actually asymptotically approach a line, which is the line where the first coordinate is 2 times the second coordinate. So it's like the line where x1 is 2 times x2. And so what's useful about that is that even though our solution is kind of complicated looking, we can actually draw a rough sketch of it pretty easily. So basically what would happen is we would start at 3, 5, and then we would approach this line asymptotically. But what happens as t goes to minus infinity? As t goes to minus infinity, the e to the 5t terms go to 0, and it's the e to the minus 2t terms that matter. And in that limit, you would approach the line where x1 is minus 3 halves times x2. And so from this, we can see that the solution looks something like a hyperbola between those two lines.